Hi, everyone. Welcome to Foresight's Molecular Machines group. Really happy to have so many of you here and still so many joining. Before we hit the road on today's guest, I do want to make you aware of a bit of housekeeping. We have our Molecular Machine System Design Workshop coming up again this year, September 11 and 12. And it's going to be in San Francisco again. And it's going to kind of bring together a few of the most outstanding projects from the last workshop, including a few new folks that have recently made a ton of progress and really making progress on molecular machine system design. And so if you're interested in joining, the applications are already open online. Just say that you're a part of this group and then we can process you. And I'm going to share the application form here as well in the chat in case you're interested. All right, cool. That's enough of housekeeping for me for now. Today, I'm really, really happy to have Abhishek join us. And Abhishek is joining from ASU, and he'll be discussing molecular and Brownian dynamic simulations of rotary catalysis in molecular motor. It's quite a handful. Thank you so much for joining. I'm also going to share a little bit more info about you here in the chat so that people can follow along and learn a bit more about you. But for now, the stage is yours.
Okay, thank you. So thanks for having me. And I think I have been participating in the talks of this working group for so long, at least for several months now. And I was really inspired by all the work that is presented here. So I felt like it won't be too bad to show some of my work and then see how we fit in here. So, okay, with that then, here is a little bit of my group. We are literally very young group. So I'll be going up for tenure this semester. And so, yeah, like we have our primary workforce is what we call molecular dynamic simulations or a computational microscope, as we like to call it.
I think you still need to share slides. They're not currently shared.
Oh, really? Oh, oops. Yeah, too bad. I was just talking to myself and that would be such an embarrassment on the recording, but here we go. And you can see the slides now. Okay, so this is, of course, my group right now. And more or less, the work that we do is around molecular modeling, something that we like to call creation of a computational microscope using a particular tool called molecular dynamic simulations. So most of the work that I'll show today is a way of using molecular dynamic simulations with certain theories in order to model movements of molecular motors and possibly directional movements of molecular motors. With that, let's dive in. So a brief introduction of molecular dynamic simulations. A number of us might actually know what it is, but let me quickly tell you, it's nothing but solving the Newton's laws of motion for an n-atom system. In order to solve the Newton's laws of motion for an n-atom system, you need an energy function. That energy function is, of course, very complicated if you look at it from the quantum mechanical perspective, but then people have made simplifications of that, and we assume that a molecule is composed of atoms which are like beads with point charges and charges with a certain amount of volume to it, which are connected to each other by springs. And each spring has a spring constant. So it's essentially a coupled oscillator. Any molecule is assumed to be a coupled oscillator with a little more sophistication to that. Let me not get into that today. And then the derivatives of these energy is what gives you force. And these forces are what drives dynamics in the system. Now, it turns out there are n atoms. We'll have to solve n-cubed equations. So we can actually end up solving these coupled equations of motion in order to, let's say, determine the low energy form of a particular protein. However, of course, these are room temperature simulations. So at the molecular level, room temperature simulations are not deterministic. The forces are not just force equals mass times acceleration. There is a noise or a stochastic part to it, which we all know. And that needs to be also taken into account, and which is done by some sort of thermostating of the system, which we do. But putting all of that together, the net outcome is something like this. We can start folding proteins, for example, start something that is highly disordered, and then try to find the global energy minima or the potential energy minima of these proteins, of a particular protein, by solving this simple Newton's laws of motion. Nowadays, there's something that is called exascale computing that has come up. The largest supercomputer in the country is actually in Oak Ridge. It gives us the opportunity of computing 10 to the power 18 double precision operations per second. 10 to the power 18 is a very unique number. I mean, it's not like we have to think about the number 10 to the power 18. Maybe people can think of 10 to the power 18 as 1 millionth of Avogadro's number, so to speak, a micromolar kind of a solvent, if one has to think of it that way. But that means that for that many number of atoms in principle, we can run these sort of big simulations. The kind of tool that we work with, we develop is called NAMD or NAMD. And yeah, so this is kind of the tool that we have been developing, that my advisor, Professor Klaus Schulten, has developed in Urbana-Champaign for close to 3 decades, after which we continue working on that. Now, of course, then there is a big problem. The problem is as follows, is that there are computational limits to these kind of calculations. This paper came out where they say that if you just think of CPUs for the time being, I know, of course, there are GPUs which are more sophisticated, that if you have an n atom system, n being a billion, which is close to a spherical cell, and you have 10 to the power 19 flops in the computer, that's how fast your computer is. And the time step of solving the equations that I showed you before is of the order of a femtosecond. Let's assume that that's the fastest movement that we have in our system, which in the nuclear world, not in the electronic world. In the electronic world, of course, changes happen much even faster than that. But if we consider atoms to be solid spheres, then that's not a bad assumption to have. Then, and let's try to figure out an event that is happening over 2 hours. Like the real event, the real wall clock time of the event is 2 hours. Then if you plug these numbers into this calculation, it says, which is of course like the doubling time of bacteria, just for an example, it's going to take 10 to the power 9 years to simulate using just CPUs with this entire object. Now, of course, there can be simplifications that can be made here. These 10 to the power minus 15 seconds can be 4-fold, 5-fold, possibly 100-fold faster. And we will talk about that in a bit. These machines will become 10 to the power 19, hopefully in days to come. We are not always interested in simulating 10 to the power 9 atoms. So that comes down also. Let's say one is interested in simulating 100 atoms or thousands to at least thousands of atoms, 10 to the power 3. So that also brings this number down to in the scale of years, not in the scale of weeks to months. And how do you, and essentially what I'm claiming is, and as experts of molecular motors in the audience, you can think of your system, the system size. Do try to think of the surroundings also, because this is not just the system, this is system as well as the surroundings. It might be a very small motor, but the action of the motor is determined also possibly by the surroundings and the time scale over which a turnover is happening and things like that. Once we do that, like we find that essentially years of computing time with the best of supercomputer in our hand, and assuming that we are utilizing each and every node of that supercomputer year long, can we achieve this, which possibly is not possible. So this is one of the major problems in using molecular dynamic simulations to study molecular motors, despite being in principle be able to do this thing. So now then, what are the way outs? So there are a number of way outs of this kind of an issue. We have 2 of them, like in my team, according by my training. And of course, a part of that has been MR Flood, who is in the audience today. So we have had the opportunity of handling this problem in 2 different ways. I'm sure there are other colleagues who would handle this in a few other ways, but we have 2 different ways, and that's what I'm going to talk about today. The first one is, one can actually end up using experimental data, knowledge of experimental data, very raw data of different states of the proteins, and use that data to drive the dynamics of the proteins towards that data. Of course, the dynamics in doing so is not going to be the most realistic dynamics, but it'll give us some idea. And after that, there's a huge amount of work that we have done in figuring out the realism of the dynamics as they are being biased by the experimental data. So there are a number of experimental data with which we work often, namely NMR and X-ray crystallography, cryo-EM, sometimes even imaging data. I'm not going to talk about the methods for this, but these kind of methods are available, where the basic philosophy is that a part of the driving force of the molecular motor, that information is being derived from the experimental data itself. And I'll give you a small example of that. But this generally speaking, this belongs to the house of Bayesian inferencing kind of methodologies. I just drop that word and move on. But Bayesian inferencing methodologies can be utilized to integrate experimental information with molecular simulations and get around that bottleneck of simulating events that are of the milliseconds to seconds time scale, taking years. One can do that, but like it's not a very there are a number of ways. First one needs to figure out the dynamics, and then one needs to essentially recapitulate the kinetics. And we'll talk about that. So that's one way, using experimental data to drive movements. And then figuring out the quality of that movement by de-weighting that experimental data, or by removing the effect of the experiment. The next method is solving Brownian dynamics equations. So if I may ask a question to the audience here, and they can put it. So what molecule are you seeing here? Can you guess what is this? I've given you a molecular structure of a molecule. Is there, can anyone guess what kind of a molecule this is? Biomolecule, organic molecule, organometallic complex? You can either unmute or you can put in the chat. I'll count to 5. 1, 2, 3, 4, 5. Let's see. Did anything come in the chat? Nothing.
Nope.
Okay. Nope. Okay. Fine. As it's not supposed to be, because by looking at a bunch of atoms this way, it's very, very difficult to figure out what molecule are we looking into. However, if I just change it, now you know what molecule we're looking at. So essentially, reduced space is very, very important. We often end up learning things in reduced spaces. Our interpretations are often in reduced spaces, in collective spaces. So as soon as I converted this all-atom picture to the picture of secondary structure, you can realize that it's a protein. So essentially, equations can be written, namely those of Brownian dynamics equation, where instead of looking into the movement of every atom, one can, like together with looking into the movement of every atom, one can start looking into the movement of elements of the system by still being true to the fact that the elements are composed of atoms, that these secondary structures, that these collective variables are composed of atoms. But ultimately, the dynamics is that one is interested in is happening at the level of these larger scale elements, these coarse-grained variables. That is the next methodology. Again, a very established methodology. Different people have different variants of applying it. But ultimately, this is what ends up becoming something called a Langevin dynamics, which can be simplified to Brownian dynamics, where one is interested in, and let me write out the equation. I've not written out the equation for you. Mass times acceleration equals the derivative of an energy function times noise, essentially. Times, and there is, of course, plus friction. This friction is coming from the surrounding, possibly, and times noise, plus noise, which is coming from the temperature, the thermal disorder of the system. Now, this U is a little bit different from the U that I showed you for the molecular dynamics, because this U is an ensemble average. It's an average surface, which is averaged over the molecular configurations of the system. So it is more like a smoother representation of the surface than what normal molecular dynamics does. Therefore, if you start running simulations with a smoother energy surface, you can take bigger steps. And that is what gives us acceleration and possibly insights into timescales that are not possible with normal molecular dynamics. That 10 to the power minus 15 seconds time step that we were talking about, that issue gets overcome, and one can go up to picoseconds now, 1,000 times more in these kind of simulations. Okay, so these were the two methods. Now let's start doing some science with these two methods. So first, let's do some simple movements. Let's start out with, so when I was a postdoc in Urbana-Champaign, I continued working with Amar, and Amar had this issue of, he had these sinostar rings, which are essentially rhodaxanes. And in fact, this problem came a little bit later, but let me tell you the story in a way that follows a narrative. So the problem is that you have this sinostar ring, and this ring needs to be threaded on a tetrazine track. So now, this sinostar ring normally can also make dimers. So now the problem is that we want to resolve is, what is the pathway of the threading of sinostar on this tetrazine track? Is it going to be like, does the dimeric property of the sinostar itself, is that going to be of relevance when the threading event happens? In which case, the pathway would be, this would actually engage, this would thread as a dimer. So like this dotted line is essentially is a representation of an interaction between two cyanostars. It can be, of course, imposed by putting a linker, but one can even think of not having that because there is pi-pi stacking interactions between cyanostars. Is this going to be a key player while this threading event happens? In which case, there will be one mechanism of threading where the first sinostar goes in and the second sinostar essentially gets attracted towards the first sinostar. So the barrier of the movement of the second sinostar is actually tuned by the presence of the first sinostar interacting with the tetrazine ring. As opposed to, it can easily be that when this threading event happens, the dimerization properties of a sinostar is not going to be as important. So the first one comes in and the second one is important. Is essentially a different event altogether. The second sinostar coming in and displacing. So these are two possible mechanisms. And this movement, Imar coined as inchworm movement. If you see this two rings and how they are moving together, they're contracting and expanding. If I keep moving the tetrazine ring on this side, this will be contracting and expanding. The movement of like an inchworm on a surface, which again, there are biological equivalents to those also. So now, how can we, using molecular dynamic simulations, using molecular modeling, figure out the difference in mechanism between these two pathways? So then our journey began. The first thing we did was we determined the structure, and this was back in 2015. I was still a postdoc then. The first thing we did was to determine the structure of a sinostar molecule. Now, it turns out that the sizes of these molecules are in the borderline of something that is macromolecular. So therefore, one can use traditional structural biology methods. One can conceive of using that in determining the structure of these molecules in order to resolve the whole molecule disorder in the system. Because there's a lot of disorder. There is dynamics in the system, and we want to look into the dynamics, and structural biology tools are often very, very good for determining the dynamics, the disorder coming from the dynamics. So we started using something called Phoenix, and we got a very, very poor refinement. Then using molecular dynamic simulations driven by the experimental data, my method number one that I was talking about, where I will drive molecular dynamics with experimental data, I found this huge ensemble of structures diffusing all over space. And only a part of this actually clusters with the diffraction data that MR had collected, very high resolution at 2 angstroms. And then once we refine this entire ensemble determined from a molecular dynamic simulation against this diffraction data, we get these two conformations essentially of sinostar. And now that was a single sinostar, not a double band. So as soon as that happened, then in the next paper, we then started looking into the binding of a sinostar dimer with on the tracks. It was not tetrazine, it was diglyme. So there were basically the diglyme binding of sinostar dimer at different temperatures. So we could get this huge ensembles of structures. Out of this, we had two findings. The first thing was we could now determine the structure of a sinostar dimer with diglymes caught in the process of binding, not just a bound diglyme, but one that was here, which we were seeing very clearly in the molecular dynamic simulations, something that was going in at different temperatures. The next thing that we found was that there are different chiralities of a sinostar. This is called up, down. And what are the different propensities of each one of these chiralities in a monomer and a dimer? And we found that these kind of drumming motions in a dimer is actually energetically more unfavorable than in a monomer. So by doing this, we kind of figured out the free energy landscapes of individual components and individual interactions that contributed to the inchworm motion that Imar was conceiving. There was no proof that was there still. But these were all the groundwork that we needed to do in 2015 and 2016. So when 2018 came and Imar had this data of threading, how can we start interpreting that data? Okay. So then the next thing that we did was, this is where I think molecular dynamics helps. We started, Imar and me, we worked together to come up with an energy landscape model of the threading event by using information from the molecular dynamic simulations that I showed before and some empirical information that Imar had based on changes in the circular geometry traces and past molecular dynamic simulations, as well as some sort of dissociation constants. So the association and dissociation constants gave us idea about what is the low energy, what is the energy wells, so to speak, and the barriers we determined from the molecular dynamic simulations that we had done before, verified with MR cyclic voltammetry experiments, where the rate of switching or change of cyclic voltammetry peaks gives you an idea of the rate of the redox processes. So then, once we had this, so now in principle, we have an energy landscape of the entire threading process, following MR's intuition of inchworm. If it was an inchworm movement, then arguably this is a landscape. Of course, there will be error values around each one of them, which we, in this PNAS paper, we chose not to take into account, or we felt like the errors in this creation of a landscape are not detrimental when I compare this to multiple mechanisms. The errors are lesser than differences in multiple mechanisms. Okay, so now then, when I have this landscape, what do I do next? So next, this landscape goes into my Brownian dynamics equation. The random fluctuations, which are often determined, the bounds of which are determined by the diffusion coefficients, often called the diffusion fluctuation theorem. MR had very good measurements of those. And with that, we started doing a small Brownian dynamic simulation. Let me explain to you what you're seeing in front. A Brownian dynamic simulation here is how will a state change from, let's say, one state, one energy level to another across this energy barrier. And again, the width of these barriers also we were very, very careful about deciding. We'll show that in the next slide. So what I'm showing here is how a population of cyanodimer with tetrazine is moving from this state to this state. Please don't assume this to be any dot here represents a population, it represents a state. It is not a geometry. I'd like to mention that a point here means that I am starting here and I'm going here. It does not mean what is the clear interaction inside that is not a part of the simulation. That has already been embedded in the U, which I have determined from the molecular dynamics simulation. Now what I'm trying to do is a kinetic model of if a population starts from here, how long is it going to take to reach from here to here? Or for any one of these barriers, as a matter of fact. I'm showing you the rate determining step here. So one thing that we see is that every time that there's a statistics here. Not that I'm starting with the red. So red means the highest energy. I just, for the sake of presentation, normally we did from the left to right. But for the sake of presentation, I'm starting my population on the top here. And I'm seeing a major part of the population is going to the blue on the right, the blue minima here. And a minor part also goes to the left. But everything is not going together. There is a essentially the idea is that there's a statistics. There's a population distribution, and not just because this is lower energy than this, not that the entire population is going to shift. Again, it's thermodynamic partition, very clear, very simple, but we all got very excited to see that in the context of a realistic application. Okay, so now that we can do this Brownian dynamics, now let's compare these two possible mechanisms. One more thing. So with Attila Szabo, advisor Professor Schulten, he had come up with an equation for determining mean first passage time by integrating over the Brownian dynamics equations. And that essentially looks like this. So what is the upshot? What do we need? What do we get out of these kind of calculations? We get mean first passage times of a population of statistics moving from one state to another. As long as we know these states, we can find the rates. We can find explicit times by knowing the energy surfaces. And so we had these two different designs that I showed you. One was this inchworm movement, and the other one is this monomeric movement. And now we actually we can create this energy landscapes and project our reaction coordinate to position space, exactly where we are with respect to the thread, and can come up with mean first passage times of each one of these steps. To observe that the inchworm movement, the slowest time is of the order of 10 to the power minus 2 seconds, as opposed to the single monomer. If that were the mechanism, it would be of the order of seconds. And now, of course, these rates, like at the order of 10 to the power minus 2%, these rates of threading matched very well with MR's measurements. He was seeing like close to like thousands in a second. We are telling hundreds in a second. Still, an order of magnitude off. But clearly, inchworm is the movement that gives a landscape. That inchworm is the movement, the underlying landscape for which supports the kinetics that circular voltammetry was showing us. I think with that, then, so that's kind of an example of a simple movement. Then, of course, with Jan Jappesen, one of Imar's colleagues in Denmark, the plan was, can we now translate these landscapes to study motors? Now, the next question that often comes when we get into motors is, and I'm so glad Dean Astumian is here. The last time I was giving this talk, a part of this talk was before Arya Warshal. And Arya told me, talk to Dean and show some of your works. I'm very happy that I can show that to him today. So then the next big problem is, as Dean showed us in so many of his works, is a motor moves between two surfaces, and we have to figure out a mechanism of flashing the motor, like a model of how do we move from one surface to another. And that was something that here we did not have to worry about, because essentially we were moving on one surface. This is not a motor, right? There is no idea of a directional motion. This is just threading. Of course, there is a certain stimulus that Imar has used using voltages that I kind of sidetracked, but still the idea here was not to get directional movements. Oh, sorry. And now, but as soon as we move to motors, the first problem that a molecular dynamics simulator will have to think of is, how can I model flashing? And so then that is where we came up with another methodology. Let me introduce a third method, so to speak, where we take, so again, before when I introduce a methodology, I should say I make a simplification. The first simplification that I make is that the time scale at which the flash is working is much, much faster than the time scale at which the motor is operating. So essentially, the transitions between the rate of the transitions between the multiple surfaces is actually faster than the transition along the surface of a motor. Allow me that assumption. That's my first assumption. In doing so, and then I start with a very concrete example of a chemomechanical motor, where the flash is actually a chemical event. It's a reaction. Let's say ATP hydrolysis. So then I can come up with a molecular dynamics simulation methodology where I separate out my chemical events from my mechanical events. Don't worry about what this jargons mean inside these boxes. Doesn't matter. I'll some sort of molecular dynamics at one level. So the idea is to figure out how much chemical energy is stored by the system using one kind of methodology, and how much energy is being utilized by the system to undergo mechanical deformations. And then compare this with this to figure out an energy conversion efficiency, and also to figure out turnover rates. But my biggest assumption that, again, need not work in so many places, but will work in a number of places, and very interesting places, as I'll show you, is that the chemical event, that my trigger, is actually faster than my stimulus is actually faster than my movement. So with that, then let's look into one of our favorite motors, ATP synthase. This is not the F type, this is the V type. So this is an anatomy of the motor, if I may. This motor is composed of, it's a hexameric motor. It is composed of 3 A type of units and 3 B type of units. Often these are called alpha and beta in the reversed order. A is called beta, B is called alpha. And you have 3 pockets. One of these pockets is an empty pocket, which is where a fuel ATP can come inside. Then there's another pocket that's a bound pocket, where once the ATP comes in, the empty pocket closes and becomes a bound pocket. And then inside the bound pocket, it even tightens further to become a tight pocket, where the ATP now undergoes hydrolysis and becomes ADP plus phosphate. So it is essentially, and as that happens, there's a rotation that is induced in the center of the molecule. Let me then, and this is how the pockets look like. This is the ATP molecule. It is not yet bound to this pocket here. Here this is bound, this is completely bound with this lysine engaging. And here, there is a famous molecule, part of the protein a famous arginine called the silver finger, arginine finger. Once that interacts with this particular gamma phosphate gets cleaved off. So if I simplify, so now coming back to this particular, I might have stolen this from one of Dean's papers, and not now, 5 years back. And so what I'm suggesting is that this transformation is ATP hydrolysis. This is my chemical transformation. And this is what I'm going to be first modeling. I will not be interested in the pathway of this transformation. I will simply capture a state here and a state here. I will not be interested in how this transformation happened, because that is possibly a fast event. I right now might be in working together. We can come up with a way of doing this all together. But right now, I'm assuming that I don't know the mechanism of this particular pathway. And then Dean has a comment for let me finish, and then I'll continue, and we can I like that conversation to happen. So once this happens, so this is the model that we had created back in the day. And so then once this happened, now I'm in this state. This movement I will be able to capture using molecular dynamics simulations. And possibly after that, the product release happens and the system resets back to its original state. So this is the thought that I have. So how do I do this now? How do I realize this theoretical model into computing models? So this chemical change that I have. So right now, I have, let's say I have started an ATP synthase system where the chemical reaction has already happened. And after that, it has become ADP plus phosphorus. And there, this side is empty. Now, let me take my products out of the system and introduce an ATP inside the system. In doing so, what I'm doing is I am destabilizing the system by 10 kilocals per mole as I remove the product out of it, because there was a lot of interactions that had broken. And I've introduced a very small amount of energy by just letting an ATP meander around this pocket. So overall, I have increased the energy of the system by 8 kilocals per mole. My assumption is that chemical energy is not like lighting up a match inside this. Chemical energy will have to be stored for a certain amount of time so that movement happens. And the assumption that I'm making is that chemical energy that is stored in the form of binding affinity changes of these pockets. And it is because a chemical energy takes it's very easy to release that and dissipate that. However, these motors actually work on the timescales of milliseconds to seconds. So it will have to figure out a way of utilizing these energies, of retaining these energies as rotation, so that it can go towards rotation and not just dissipate in the surroundings. And the way of doing that is possibly by changing the binding affinities. So as soon as now I introduce, I now start I start from this state, my simulation, where I have removed my products and I've introduced a new reactant. My overall energy has gone up by 8 kilocals per mole, and these are explicit calculations. I am not making them up. we have done very strong free energy calculations to figure that out. Once we have done that, then you let your system relax. Then essentially what you see is that simply as a response to the fact that an ATP has been removed from a T pocket and an ADP has been inserted in an E pocket, simply as a response to that, the molecule moves. Right now, of course, this movement does not mean anything. Now let me, and the energy change of that is, as I said, around minus 2 kilocals per mole. Now think of it. I have given my molecule 8 kilocals per mole of energy, right? Like if you believe in my assumption of changing the binding pocket affinities, I have increased the energy of my molecule by 8 kilocals per mole, and this movement is only utilizing 2 kilocals per mole out of that. So it's a very, very poor motor. It is not utilizing, it's just like 2 out of 8. 1/4 of the energy is being used up, and the other 3/4 is kind of dissipated in the surroundings. Now let me do the same movements, the same modeling, but introduce a stalk in the middle. And now this stalk is actually rotating in response to the movements of the proteins on the sides, which I have induced by simply changing the binding pocket conformations. And now if I compute the free energy change of this as opposed to -2, this has become -6. So if I assume that 8 kilocals per mole of energy is used in my going from my ground state to the excited state, and we'll talk about that, Dean, as in the discussion. Is that a right way of thinking about it? It's not completely right, I know that, but to the extent that I can do in the make a model in classical simulations, my assumption is that the binding affinity changes is being used up for mechanical movement, and the binding affinity change is a representation of the flashing. Then I see that 6 kilocals per mole out of that 8 is used up for this movement. And there's an improvement from 25% to 75% efficiency by simply introducing the stalk here. So this is where the concept of a power stroke also comes in, actually. And I'll go to the power stroke in a bit. So now I have shown that this 25%, so I can write a thermodynamic cycle here. I can come up with the thermodynamic cycle of what is the energy that is required by the binding affinity changes on this side and the mechanical energy on this side. And I can find a ratio between them, which I say is 75%. So I am making an assumption. So now then, following my model in its correctness or incorrectness, what I have now done is I have modeled hydrolysis or the effect of hydrolysis. I've done my rotation. This is my rotatory catalysis. This reaction coordinate can safely be an angle if we so choose to. And the angle can be 120 degrees. Now I need to figure out the mechanism of product release in order to reset the system back. And that is then was done with C. Okay, now another thing I have to now say is that what happens if this product is not released? I had assumed, I have shown you this surface. I went up here and I have here. Let's say the product is not released and I churn my movement from this side to this side. Still, like I artificially do that. What happens is then, so I churn my movement. Now, instead of the energy going down, because my product is there and have enforced my product inside my reaction chamber and still made my rotation happen. 1 to 175 is what you call an image index. Let's not worry about it. Again, this is safely a rotation of 100. The energy, instead of going down, actually goes up. So it is resilient to the movement. On the energy surface, when the product is present here, my motor does not move. My motor can only move when this product is released, and then this motor moves to the surface. So now, and this of course we also experimentally verified, and in doing so, and along this lower part of the system, what we found is that there's a certain amount of elasticity in the central stalk. It does not move like a rigid entity, and I'll show that to you in a bit. But let me go back. So now, dear, if I may, what I'm trying to now do is I'm trying to say that this is a molecular model representation of a theoretical surface that looks like this, where this is my hydrolysis step, this is my rotation step, and this is and after that, I have to essentially remove my products to come back to the ground state. This is not completely correct because this state is not the same as where I started out from, but at least it has some flavor of this mechanism. Now I still need to correct for this part. I still need to come back to my ground state. I need to know my product release that I haven't shown you yet. But from molecular dynamics simulations, possibly I can resurrect some parts of these two surfaces that we're talking about. Like in other words, this could have been a bistable switch. The motor could have gone back and forth without any directionality, but paying a huge energy cost. Rather than doing it, I do ATP hydrolysis, change my binding affinity, and now my motor moves in a direction very clearly. It's energetically favorable, 120 degree anti-clockwise. Has to happen. Kinetics can be a different story. But so in that regards, it's a kind of the first a manifestation of this kind of a thought process here. So then there are some papers that I need to, of course, cite, which where the rates were measured, the rates of these transformations. Now let me tell you a little bit about the timings of this. So now that I have the process, I have this energy landscape, I can figure out the times using the same methodology that I did with MR, essentially. And now you see that there's a huge rate determining step where that has to do with these amino acids. So a positively charged amino acid means blue, negatively charged means red. And these, if I go back in my movie, then this is where, like, there's a lot of electrostatic repulsion that needs to be gotten over in order to come here. And now there is an idea of power stroke, and my understanding of power stroke is the following, and do correct me if I'm wrong, is the fact that there is a local elastic storage unit that for the longest of time, the crystallographers said that there is no local elastic storage unit. This thing moves entirely as a rigid body at the ratchet. Of course, like essentially the ratchet moves with no local elastic storage. Why? Because the crystallographers who found these intermediates are always seeing a very stiff form of my stalk. But the intermediates, as we move through this, there is a way the stalk need not be stiff. It can actually have an elastic torsion, which single molecule people actually found. And then it can relax back to its ground state in each one of the minima. So therefore, there is a possibility of local elastic energy storage while this transformation happens. And those storages are basically the energy differences between these local minima that we found after doing the molecular dynamic simulation. So essentially, it is a combination of power stroke mechanism and ratchet, Brownian ratchets, which previously people assumed this to be a smooth thing like this. But because of the jaggedness of this free energy landscape, there is a local elasticity storage. That's what we ended up finding. So now, how much time do I have? Okay, so we are almost to the end. So then we found, of course, the mechanisms of product release. And let me see if the movie, if I can show the movies. There are two different pathways of the product releasing. So now I'm coming back, I'm relaxing my back to the system. So this is a phosphate group that is coming out of this object, because the phosphate groups release first. After that, ATP releases. That's what we found after the ATP hydrolysis. And oops, this is a wrong place to be. Okay. So now then, I found the entire mechanism of rotatory catalysis by using chemical stimulus as a change. First, ATP hydrolysis happens, then it becomes ADP plus phosphate. Then still no rotation, still no rotation. This is the center stalk. Then a phosphate goes out, still no rotation. And ATP comes in, and only then does a rotation happen. And then ultimately, the rate determining step is the ADP going out. So of this, essentially, this step is what is the, this to this is what is my charging step, so to speak, is what is my flashing step. And after that, molecular dynamic simulations can capture this entire business. Now, this is just one example of stimulus, and I will not go into, but there are so many others that with molecular dynamic simulations, we have been able to partially capture. One is using redox kind of changes, where you change the redox states of the iron sulfur clusters and you see binding and unbinding. Oh, actually, first this one, the redox changes, where you change the redox state of heme groups and you see how a particular motor moves from these two sites. Very, very directed movement. You can change the redox state of some sort of iron sulfur clusters and open quinone. Instead of ATPs, you can think of quinones as a substrate, as a fuel, and that can happen. There is, of course, the famous proton gradient as a stimulus, which we know is the searing of the ATP synthase, the transmembrane part, that can also be simulated using this kind of mindset, this kind of methodology. And yeah, so essentially, the assumption is that my chemical process is decoupled from my mechanical process, like in time, and the chemical process is fast. So I can capture my chemical process as a binding affinity change in this kind of cases, as a pH change in this kind of cases, or as a change in the local charge environment in the redox state. And then let my molecular dynamic simulation run to see whether my movements are happening in a direction or not in a direction. And I think I am already over time, so I will stop here. I would have loved to show, even after doing this, what is the problem? Because even if you, despite having the best of motors, when you take this into a reactor, I have like in my subsequent slides, let me quickly show that, and then I'm going over time, I understand that. So is there any need of motors in reactions? Do we even need the best of motors? Here is an example of a photosynthetic reaction, which is where we want to. Photosynthesis has 5 different kinds of motors, ATP synthase being the last one. Each one of them is 100%, is close to 100% efficient. However, if you take light energy and convert ATP, I'll convert that to ATP, and we kind of constructed an entire model of a photosynthetic organelle. Let me not spend time on that. Let me go to the last slide. Okay, if you construct an entire model of a photosynthetic organelle and find out the activities of each and every motor in that organelle, you'll see that every motor is extremely, extremely efficient in terms of thermodynamic efficiency, a little less so for kinetics. But when you put them all together and you start making a computation of how much ATP is generated by absorbing a certain amount of sunlight, you find that only 10% of sunlight is being converted to ATP. 90% is lost. This is despite having the best of motors. Why? Because the 90% of the loss is coming from substrate channeling. The product of one motor is the reactant of the next motor in that entire network. A lot of energy is lost in that translation of, in that pushing of the reactant from one motor into the product of the other. And that is where nature loses a lot of its energy. So despite having the best of motors, once we scale things up, it becomes very, very difficult. So we, in fact, tried to, and again, for each one of them, we had to create energy landscapes. We made an artificial system where what we did was we packed our membrane by enhancing the proximity of the motors, so that this diffusive loss of reactants going from the product of one motor, which is becoming the reactant of the next motor, that becomes lower. And by doing so, we indeed So these are different stoichiometries, and the color scale is the number of ATPs generated by this reactor. It's called a chromatophore, just for edification. So in this chromatophore reactor, if you increase the concentration of one kind of motor, these are again not ATPases, these are different kind, like light harvesting complexes, and the name doesn't matter. What we indeed found is one can make a motor that is 24% efficient instead of 4 to 10. More of the light energy can actually be channelized into ATPs by bringing things close together. But a funny thing happened, and that's what I want to end this discussion. As soon as, so this motor works under low light conditions. As soon as we changed the concentration of light, made it high light, and then brought it back to low light, our bioreactor broke down. So essentially, nature chose to make a network of motors in a way that it is happy with this 4 to 12% efficiency, but it's robust across a range of light conditions. As soon as we overtune this reactor to make more ATP, we are compromising on its ability to kind of adapt to different conditions. So with that, then I would like to draw, and this is exactly the final problem. We need to generalize this. Anything that I showed you today were all single molecule models. Until and unless we generalize this to complexity, it is very, very difficult to kind of seek the merits or demerits of the fundamental theories that we have. We are all working in this space. The theory actually in principle covers all of it. Can we do the shake hand? And that is the biggest problem we have right now. But definitely we need to do it. Otherwise, we cannot scale from a single motor level generally to a motor network level. What might be the properties of a thing that we're learning at a single molecule level are not doesn't give you the entire story. So with that, thanks for your patience. And I know I'm over time, so I'm happy to answer any questions.
Wonderful. Thank you so much. Really, really appreciate it. This was fantastic. Let's maybe start with, if you want to kick us off with your questions.
So Abhishek, can you go back to the two flashing surfaces from Kolomyski and Fisher? Yeah. So the problem here is that you're making an assumption that, well, basically you're treating chemistry as if it were light. That ATP happens at one point, that ATP binding and hydrolysis occurs at one point. I think it's L-1. And then that the release occurs at a different point. But of course, we know from microscopic reversibility. So recognize that light is governed by the Einstein relations for absorption and emission of energy.
Of course.
And the conditional probability for binding, for absorbing a photon in the ground state and going to the excited state is exactly equal to the conditional probability for absorbing a photon in the excited state and going to the ground state.
Absolutely, yeah.
Right. And of course, that's not true with thermally activated processes.
Absolutely. And I agree to that. And in fact, the modeling that I showed, I don't, at one level, I don't take into account this pathway. And I completely understand that there are relaxations and it is not a vertical pathway. And it does not matter at one level as long as I somehow reach this state. That's my point.
Yeah. Okay. But the point is that if you take this model and put in microscopic and put in a model for up and down that is consistent with microscopic reversibility.
Yes.
Then you find that by changing kinetic parameters, the kinetic asymmetry, if you can get this to go to the left or to the right with ATP hydrolysis, that the power stroke has absolutely nothing to do with the directionality.
I see.
That's a deductive fact.
I agree. And in fact, that was also what Arya was telling me. So the reaction coordinate is chemomechanical. And so my reaction coordinate that I have chosen in order to come up with these structural changes that I see is purely mechanical. Unfortunately, I do not have a way of constructing a chemomechanical reaction coordinate. That is exactly the reason of the assumption that I make in doing. Now you have a very, very interesting point. You say that if this reaction coordinate were chemomechanical, then it is possible that on that surface, on that reaction coordinate, the surface would definitely look very different, and it might actually look a lot smoother or
No,
not.
no, no. The surface would look exactly the same. Only the up and down transitions.
I see because because it is because because your flash is now a part of the reaction coordinate. The flashing
Well, the
process
flash has to be. And so this was, so I'm sure that you've seen Aries 2D,
Yeah.
chemical and mechanical rotation for
Yes.
FOF1 ATP synthase.
Mm-hmm.
And that is the essence. So here, this description is one in which you deposit energy.
Right.
And then
Right.
you dissipate it by a conformational change.
Absolutely.
And my point, and Aries, is that whole way of describing it is just plain wrong.
I see. Yeah, and that's why I wanted to have this conversation, because some of the kinetics that are coming. So how do I say this is right or wrong? Then I have no way of saying this is right or wrong. The only way, theoretically speaking, none.
So
I can always match with it.
For example, David Lee's, Wilson et al. When you try and make a model with a power stroke, you find that that David's actually goes in the direction opposite to that predicted by a power stroke model.
I see. Absolutely. And yeah, and so that's true. And this will become more and more wrong. My way of doing these things will become more and more wrong as the system size becomes smaller, as we go to more small molecule motors.
But even at the size of an FOF1 ATP synthase.
That is correct. And even though I can somehow save myself with some single molecule experiments, but I know, and this is essentially the reason I chose this theoretical model that I'm choosing, is because my computations allow me to make some sort of inferences based on that, on this theoretical model. I completely agree. The other model is a lot like your model, and I've seen your and Arya's model with the coordinate, with the reaction coordinate, where the flash is a part of the reaction coordinate, and essentially, but there is no computation that I can do that can simultaneously take into a kind of manifest that kind of a reaction coordinate in a simulation. Right now, so far, I had not been able to, and that might be something I was hoping that as part of this working group, I can work with you to come up with a reaction coordinate model like that. Because in classical molecular dynamics simulations, impossible. What Arya, of course, does is he has made his own very coarse-grained model, reaction diffusion kind of a model, which is where this kind of a reaction coordinate works. But that is very, very parameterized only for ATP synthase. You can't just take it beyond anything else. So I just want to have.
And so basically, you're inserting the lateral transitions, the up and down transitions, ad hoc.
Correct.
And then you're modeling the motion of the conformational motion. But if you put in correct rate constants for the up and down motion, then you get the correct behavior. You can't. I just don't see any value to sticking in we're going to increase by 8 kcal per mole the energy and put it on a conformational surface where it's downhill. So that's not the way that physics works at these.
Right, and I just, let me clarify. When I add this 8 kilocals per mole, it's not like I'm randomly adding it. What I have done is I have reconfigured the ATP and the ADP conformation concentrations inside my protein, and separately I am computing that is 8 kilocals per mole. So I don't just heat it up by 8 kilocals per mole. I have reconfigured. So I actually, what I'm claiming is I actually have a crystal structure at this particular point where I am putting my arrows.
You certainly do. And if you get to, so for those molecules that get to that point, they do exactly what you say they do.
Yeah. And what I'm claiming is that's where I start from. So I don't get into a problem where I don't have an information that is here. but I want to overcome that and work within this group, possibly come up with ideas where because I understand, of course, I will not do a vertical transition on this. It's very straightforward photophysics. So I will always be working. So I am telling that as a simplification of the theories that you have for certain problems where experimentalists offer us this location, I can use classical mechanics to at least do something like this. But
yes, so you can get a conditional trajectory.
Yeah.
But the whole essence of the problem of determining in which direction the thing goes is determining the probability of achieving that condition.
I see. Of course, that's true, because this pathway is completely garbage as far as in my way. Even in free energy perturbations, this pathway does not even exist. So I completely agree. The probabilities, my probabilities of this transition are incorrect. They're wrong, and I'm not even claiming that. And that's where I need to know. In fact, there is no modeling. I know the mathematics of this, the Fermi transitions that we were talking about, which are the vertical ones, and how do they break. I'm completely aware of those, but I have no idea of how to implement that computationally. And that is general enough. Might be we should talk a little bit more, a lot more about it, how to insert these in proper ways. Right now, my assumption is exactly, so you've got me right, that I am assuming that I know this point exactly. From there, I do this. But the directionality, you're right. So the directionality is a decision at this point, whether to go here or to go here. I don't have any idea about these kind of transitions. In fact, this two surfaces need not be on the same. There can be a z-axis coming towards me or away from me, and this can be spread out that way. And I have no way of understanding that. So yeah, and that is something that I think would be very, very interesting to learn together at one point. And I do, especially not the theory of it, because the theory I've learned from all your work, but how to implement that computation would be very, very that's something.
But Aries, I mean, the thing that we learn from looking, for example, at Aries' 2D model of the FOF1 ATP synthase is that the underlying dynamics is that of diffusion. It is simply diffusion on a two-dimensional energy surface. And the directionality arises from one thing and one thing only. And that is that when the active site is unoccupied, if you have a lot of ATP, it is more likely to bind ATP than it is to bind ADP.
I agree, but you have to also concede that interpretation has already gone in the construction of the energy surface. So the way the energy surface was constructed, which was also constructed in I would say in using very intelligent intuition and a little bit of ad hocness, a surface was already constructed for the last 10 years, which is what he has been working with. It's a heavily parameterized surface that we're talking about, that cannot be generalized beyond. So those inferences cannot be generalized beyond that surface. And the arguments.
But it does raise the question: is
Absolutely.
underlying physics that of diffusion, or is it that of elastic relaxation?
And I would say if the surface does not have elastic deformation built into it, then it will only show diffusion. And possibly
even if it has elastic deformation built into it, I mean, you can take a model of springs and put that and write an energy for every possible configuration of the atoms. And now, if it is not damped, obviously everything is governed by the elastic relaxation. If it is overdamped,
as is the case, as can possibly be the case,
low Reynolds number, which is almost certainly the case for nanoscale things.
Absolutely,
Then, despite the fact that it's made of springs, the motion is that of diffusion. It is governed by Fick's law. And then you can put in probabilities to achieve a particular configuration.
Mm-hmm. Mm-hmm.
but then it's ultimately diffusion.
Right. So the yeah, and so there's nothing to disparage that, because that's absolutely right. That's essentially textbook knowledge. And now the point is, what I was, when I meant power strokes, I was simply implying that the power stroke will control the rate. Once the diffusion has chosen the direction, the power stroke is going to control the rate of that direction. Would I be incorrect in stating that?
No, you would not. That would be correct. I
And
mean,
that is what
so the,
that is
the conformational change
Mhm.
governs the rate of the conformational change. Yes.
Exactly. And that's what I was, when I meant power stroke, I did not imply power stroke as a way of determining the direction, because you're right, the direction is already being assumed by the nature of this landscape by then, however that is being created. But what I was trying to say is that there's a huge, possibly this is a difference in the language that we got into, but I think I agree. So the diffusion will give you the direction. Why? Because the direction is already embedded in the landscape. But what I was suggesting is that the rate of that will also be determined by the power strokes, which often is by the local elastic storage. So when I was meaning power stroke, I meant elastic storage. And those local elastic storages will affect the rate once you have already chosen the thermodynamics by the free energy surfaces. And that's where I was implying when I mentioned power stroke is important. I should have said that power stroke is important to tune the rate of the system, the kinetic efficiency, once the thermodynamic efficiency or the different populations is determined by the chemomechanical reaction coordinate that we're talking about. Would we agree on that?
Basically, I don't like the idea that of storing energy.
And then again, I also don't like it. And I also don't like it. And I agree with you that now when we talk about that chemomechanical reaction coordinate, there are, I can think of two different places. Or there's a 1 minute warning and we have to leave. Then there are, I completely agree. So it's essentially a hazard for me, for the sake of generality and taking this into so many other proteins, that I have to separate them out. But I completely understand your criticism, and there is, and you're completely right there. I need to find out energy landscapes where I know a crystal structure at a given point. Otherwise it would be and so it would be so much nicer to actually come up with a way of general way, not a very highly parameterized way of figuring out this chemomechanical part by actually not assuming any storage, seeking if there is a storage there or not. Yeah, no, that's that's really enlightening. And at the same time, I think yeah, this conversation needed to happen at some point. Okay, so there are a few other things. So can I quickly? There's a stat around. Might be.
We have
but we don't
we
have
had
time.
one question by
We don't
the
have
head off, but we're already, I guess 11 minutes over. But you did get a comment here that this was the best talk and discussion someone in the presentation room has ever heard. Bravo, super slides.
Thank you so much. Thanks. I would love to answer your question if I can just. Yeah.
Yeah. How about people can write me with any follow-up questions and I redirect them to you if it's advantageous.
Thanks for the talk and also the discussion afterwards. This was a really good discussion, I think. Thank you.
Thank you so much. Thanks for your time.